Section 7.5, Graphing Quadratics in Vertex form. The objectives here are going to be to graph parabolas whose quadratic equations are in the form y minus k equals a times the quantity x minus h squared, and to find the vertex and axis of symmetry of a parabola. First, let's begin by looking at the graph of y equals x squared, which is our parent function here, by means of making a table of values. So this is always a way you can graph things, by using a table of values, but we'll see as we get further and further into this section that making a table of values is not necessarily the easiest way to graph these different equations in quadratics. So if we start with x values of -3, -2, -1, 0, 1, 2, and 3, and we go ahead and just plug these in, we're just getting the square of each of these. So 9, 4, 1, 0, 1, 4, 9. And we're going to see right away that there is symmetry. So a graph of this would look like the following. We'd have our points on the left side here, and our points on the right side over here. Let's say we go up to 10, and we're going by ones along the x-axis. Well, for this problem, our coordinates look like the following. Which at first might look like a V, but in reality what we have here is a parabola with a curve to it. So if we were to graph this parabola, there's a little curve to it, and then it loops back up. Now, what we're going to notice right away is that we see some symmetry, as we saw in the values of y, but we also see it graphically. And we can see that there's a line of symmetry right here down the middle. And thus we could say that the axis of symmetry of this equation happens to occur on the line x equals 0 along the y-axis. That's the equation of that vertical line there. So we call this the axis of symmetry. We also notice that there's a vertex in this equation, and here's the vertex down here at 0, 0. The vertex, another term for, is a turning point. And then finally, we're going to take a look and notice that the graph in this case opens upward, so we say that it's concave up. And the way to see that is to think about the shape of this. Whichever direction this faces is the concavity. So that would be concave up, as opposed to a graph like this, that would be concave down, because it opens down. Now, if the equation is transformed so that it looks like y equals -x squared, or in general it has some a value as the coefficient of x squared, the graph changes respectively. So let's take a look at some examples of this now. So first, what we're going to notice here is that when the value of a is less than 0, the graph ends up being concave down. And we can see this by looking at the graph of y equals -x squared and seeing that it opens concave down, whereas this is concave up. So already we'll notice that as if a is negative or a is less than 0 in these cases, it's going to be concave down. Now from the two graphs below, we can see that as the absolute value of a gets smaller and smaller, we're going to notice that the graph gets wider. And we'll see that right here. Here's the original parent function right here, y equals x squared. And then we'll notice here that the absolute value of a is smaller, right? It's 0.5. And notice that this graph is now wider. It's not as steep as the original graph was. And we'll notice that as the absolute value of a gets larger, the graph gets narrower. And we'll see that here with these numbers. Here's our parent function. Here's a graph with 2x. Well, with 2x squared. With 2x squared, the value of a is greater than the original value, and suddenly this graph is steeper. The wider graph is now the original. So again, as the absolute value of a gets larger, the graph gets narrower. So in general, think of a the same way you would think about the slope of a line, but really as the absolute value of a, not a. And as it increases, the graph gets steeper. Now note that if a is equal to 0, then the graph is really the line y equals 0, which is simply the x-axis. Right, if we had 0x squared, it's really saying y equals 0, and that would just be a line along the x-axis here. Next, let's take a look at how the graph can translate or shift horizontally and vertically. So first, let's take a look at the vertical shifting of the graph. And this occurs when the equation is in the following form, y minus k equals ax squared. There's no h involved here now. And what we're going to notice is this. When the k value is greater than 0, the graph shifts upward. And when the k value is less than 0, the graph shifts downward. Okay, shifts downward when it's less than 0. And we're going to see this in the graph at the right here, because clearly the k value here is 3. Right? It's y minus k. y minus 3. So 3 takes the place of k. And when we look at the red line, 3 is positive, because this negative just comes about from the original equation. The 3 is really what k is. So when k is positive 3, we see that there's a vertical shift upward of 3 units. So here's the new graph, shifted up 3 units because of the positive 3 here. Again, ignore that negative sign, because that's part of the original equation. Well, how would you get a positive 4 here? You'd only get a positive 4 here if this was y minus negative 4, right? Because k would be negative 4 here. When k is negative 4 and we have y minus negative 4, we get y plus 4. So really, this is a k value of negative 4, and we'll see that the graph is shifted down 4 units. So what we can say generally is that k indicates the vertical shift. Okay, and it's sometimes more obvious, instead of looking at this version of the quadratic, to look at it this way and to move the k over. And we can see here, because if we add a positive number here, it's going to shift upward. If we add a negative number, it's going to shift downward. Okay, so if you want to look at it this way, that's fine. But remember that this is the actual vertex form, where it's y minus k. We'll see more of this in the next section when we look at functions. Next, let's take a look at the horizontal shifting involved in the graph. And this is going to occur when the value of h is taken into account. So now let's make believe there's no k here, and we have y equals a times the quantity x minus h squared. And what we'll notice that the graph shifts right when h is greater than 0 again. So the same thing occurs as with the vertical shift. When k was positive, it moved up. When k was negative, it moved down. Well, here, when h is positive, it moves right. And when h is negative, it moves left. And we'll see that right here. So, for example, take a look at this one. The h value is clearly 4. X minus 4, x minus h. Well, h is clearly this 4. And 4 is positive. We're not looking at this sign again. We're looking at whatever's here. 4 is indeed positive. So we have to think about the fact that this is going to shift right 4 units. And there's the graph. Finally, if we take a look at the next part, though, how do you get x plus 3? The only way to get x plus 3 is to really have the equation y equals x minus negative 3 squared. And the reason I write it this way is to see that, because this is the equation or the general form here for vertex form, well, this negative 3 takes the place of h. Well, negative 3 is indeed negative, and when h is negative, we see that the graph moves left, and we'll see that the graph now has a vertex over at negative 3 instead of at the origin. Now finally here, let's look at a graph that involves multiple transformations. And what we'll notice is that the complete form, which is really also called the vertex form from earlier, is y minus k equals a times the quantity x minus h squared. Now, let's graph y equals x squared first, as this line right, or this curve right here. And then what we're going to notice is this is y minus 1 times equals the quantity x minus 2 squared. And we'll notice that this negative 1 here indicates that this is k. K is really 1. Remember, it's y minus k. So k is 1. Just take a look at the substitution there, literally. It means take it and vertically shift it up 1. Now, we're going to see that it's also shifted over 2. Why is it shifted over 2? Well, here, h is 2. See how it's minus h and it's minus 2, so h is 2. So again, the vertex in this problem is 2, 1. Here's our vertex, 2, 1. 2, 1, h, k. And that also means that the axis symmetry has changed, and now the axis symmetry is the line that goes here. Well, that's x equals 2. And if you remember, this was 2, k. So x equals h is the axis of symmetry. Remember, here's your vertex, here's your axis. Notice, same thing. So this, generically, is just x equals h, whatever h is. And this up here is always h, k. We should also note here that if the a value had been changed, the graph would have been narrower or wider. And specifically, if a were less than 0, if it were negative, then the graph would have opened downward, right? And it would have been like this. It would have been considered concave down. So example 1 says to sketch the graph of y minus 2 equals negative the quantity x plus 3 squared. So what we want to do right away is identify. Right away first, a is negative 1, right in front here. There's really a negative 1 there. H is negative 3, and k is 2. Again, How does this become positive 3? It means it's really x minus negative 3. That's what x plus 3 is, right? Remember that it has to be in the form x minus, and then this is h. And this is already in the form y minus, which means that this is k. Now, this is going to tell us that if h is negative 3, we know that the vertex is going to shift 3 units left. And then if the k value is 2, that means that the graph is going to shift 2 units up. So let's go 1, 2 units up. And we'll put our vertex right here. Again, that point is negative 3, comma 2. H, comma k. Then we'll notice that since a is negative 1, the parabola is going to open down. It's concave down. So here's our vertex. It's concave down, but the question becomes, with what points do I plot? And the easiest thing to do is to identify your axis of symmetry. Well, the axis of symmetry, we have to remember, is x equals whatever h is. Well, it's negative 3 in this case. So here's the axis. And of course it does indeed go through the vertex. So let's draw an axis of symmetry here. What we'll notice here is that the axis of symmetry splits the graph in half. So let's make a quick table to make this easy on us. And what we'll do is we'll pick 2 points to the right of the axis and 2 points to the left. So negative 2 and negative 1, those are both right here and right here. And we know we're starting at negative 3, then we'll pick 2 points over here. So we'll say that these will be negative 4 and negative 5. So we have 4 points about the part that we're looking for. So negative 2 is 1, negative 1 is negative 2, negative 4 is 1, and negative 5 is negative 2. We'll see the symmetry obviously here, and we get a graph that looks like this. Next, let's take a quick look at the intercepts of quadratics, and remember to find the y-intercept we set x to 0. Okay, we set x to 0. Solve for y. Well, that's pretty easy. But to find the x-intercepts, this is the difficult part. We want to remember that we have to set y to 0 and solve for x, but there's 3 different cases here. So we have to remember that when we set y to 0 and we solve for x, it's a quadratic. And for a quadratic, the discriminant could be positive, it could be 0, or it could be negative. When the discriminant is positive, we have 2 roots, and they're distinct. And that's what we've said already. We've talked about this with our quadratic formula and the discriminant, but graphically now this is what we see. There's 2 intercepts, or 2 real distinct roots. And they're traditionally binomial conjugates, or sometimes integer values, depending on what the discriminant value is, if it's a perfect square or not. And for the next case, if the discriminant equals 0, remember we have 1 real repeated root. Well, that's a tangent. It is tangent to the axis. A double root has a point of tangency. It is tangent to the axis. And then finally, the third case, when the discriminant is negative or less than 0, and those roots are imaginary, so they don't show up on the graph. And this graph looks like it's floating. It could float up like this, or it could be an inverted graph and float down here like this, with no x-intercepts. Remember, it has to have a y-intercept, so even though it doesn't look like it, this graph will go on and on forever, eventually hitting the y-axis, because there's some slope to it. Let's also make one final note that when we keep talking about the discriminant here, we're talking about if the equation happened to be in a form where it was in quadratic form ax squared plus bx plus c. We know that we're looking at right now y minus k equals a times the quantity x minus h squared. But if this were transformed into standard form by multiplying out x minus h, foiling, distributing a, moving k over, you'd end up with something that looked like this. And we'll see more of this in the next section, but this is the discriminant we're talking about. Okay, but it's still the same idea that the discriminant does apply in this case, because you are going to get imaginary roots sometimes, and they won't appear to show up on the graph as x-intercepts. Example 2 says graph y plus 3 equals 2 times the quantity x minus 2 squared, identifying the vertex, the axis of symmetry, and all intercepts. So let's begin by saying that k has got to be negative 3 and h has got to be 2. We can see that because k has to be negative 3 because x minus, or y minus negative 3 is really y plus 3. And here, this is just x minus h. Well, it says x minus 2, so h is just 2. And then a is whatever the coefficient is here, so that's just simply 2. Now, right away, with these variables, we can say already, well, the vertex is 2 comma negative 3, and the axis of symmetry is x equals 2. Automatic. Because again, this is just hk, and this is just x equals h, always. So at this point in time, we already know on the graph what it's going to look like. We know it's going to open upward. So really what we're focused on is like the first and fourth quadrant here. Here's our vertex. And I knew only to go down 3 and over 2. I mean, I'm going to need some more room over here, obviously, because the graph's going to open up. But I don't need any more room further down. So when I make this axis, I stop here. It just makes sense. Alright, so we got our y-axis and our x-axis. Next, let's find the y-intercept. And we can do that by setting x equal to 0. Set x equal to 0, it becomes 0. This is really just then negative 2 squared, which is 4. 4 times 2 is 8. And then subtract the 3, we're going to get 5. So the y-intercept, again, set x to 0. So the y-intercept is 0, comma 5. Not just 5. So it's up here at 5. There's our y-intercept. Now we know that there's symmetry in the graph. So what we can do already is take that y-intercept and reflect it over the axis of symmetry, which I'll draw in right here. So we're going to realize that there's a gap of 2 units here. So we'll go 2 units over at the same height. So we'll go to 4, comma 5. Again, because of the symmetry. Finally, we want to find the x-intercepts, or the roots of the equation, when you set y equal to 0. Well, setting y equal to 0 here, we don't have to use the quadratic formula. We can see that it's completed square already. It's in completed square form. We have 3 equals 2 parentheses x minus 2 squared. We'll move the 2 over by dividing. Take the square root. That leaves us with x minus 2. Add the 2 over. 2 plus or minus radical 3 halves. Now this is one of those cases where it really doesn't matter that you simplify the denominator because it's irrational. Because we really want decimal estimates anyway because we're about to graph. So if we estimate these on a calculator, 2 plus radical 3 over 2 is going to give us 3.2. And 2 minus radical 3 over 2 is going to give us 0.8. And those are the x-intercepts, or the roots. So as coordinates, I should really write them as 3.2, comma 0. And 0.8, comma 0. So we'll estimate, obviously. So here's our 0.8, comma 0. And 3.2, comma 0 is over here. Again, noticing the symmetry. We complete our graph now. So finally, let's write our answer here. The vertex is 2 comma negative 3. The axis of symmetry is x equals 2. All intercepts are 0, 5 for the y-intercept, 3.2 comma 0, and 0.8 comma 0 for the x-intercepts. Example 3 says to graph y plus 2 equals negative quantity x plus 3 squared. Now notice here, the only thing that's changed from the last problem, we're identifying still the vertex axis and intercepts, is that we have different values as our parameters for h, k, and a. So quickly identifying a to be negative 1, coming from the front here. Then we're going to have h equal to negative 3, and k equal to negative 2. And those are coming from here and here. Next, we're going to notice right away that our axis of symmetry is going to be x equals negative 3. So that's the first part. Let's do our vertex. we're going to have negative 3 comma negative 2. Now let's find the y-intercept because that's the easier one to find first. So let's set x to 0. We get y plus 2 equals negative. Now this is interesting because it's going to be 0 plus 3 in here. So this is what it's going to look like. The way you say this is y plus 2 equals the opposite of 3 squared. And 3 squared is 9. And we want the opposite of 9. So this is negative 9. Again, be careful here. You're squaring 3 first, then you're multiplying it by the a value, which is negative 1, really. So again, it's the opposite of 3 squared. So you have to do 3 squared first. Then we'll subtract 2 from both sides, getting us y equals negative 11. So 0 comma negative 11 is our y-intercept. So we've got 3 things so far. Next, we need to find the x-intercept, so we set y equal to 0. And when we do that, we end up getting the following. And what we'll notice is this is just 2 now, really. Okay, so this 0 we don't need. And when we get the 2 alone, we have to multiply it by negative 1 first here to get rid of that negative sign on the right-hand side. And we'll notice we're about to take the square root of both sides. Well, this is a negative number. It means that that's my value that I'm going to know right away that tells me these roots are going to end up being imaginary. So they're not going to show up on the graph. So it's pointless to continue. They end up becoming, if you want to try, negative 3 plus or minus I root 2. They're binomial complex conjugates. Those are the roots, but we're looking for all intercepts. Those aren't intercepts. They're just roots of an equation. There are no x-intercepts in this one. And that's kind of obvious. We should know that by now, actually, simply because of the vertex location. Negative, negative. That means that the vertex is in the third quadrant. Negative 3, negative 2, it's here. And because a is negative, it's going to open down. So are there any x-intercepts? Absolutely not. So technically, once we get these values, we realize that if this is set up somewhere in the bottom quadrants and a is negative, it's not going to end up having an x-intercept right over here as well. Or if it's in the upper quadrants and a is positive, there's not going to be any x-intercepts. So those are the possibilities we can look at for all of these 4 cases. Alright, let's continue now. The last thing we want to do is to make a table of values, because really right now we don't have enough information to graph this that well. This is going to be difficult. This is what we have so far to graph. So we could start sketching it, but we're going to realize we need points. So negative 3 is the axis of symmetry. There's our axis of symmetry. The vertex is at negative 3, negative 2. I'm going to go by negative 2 in this axis. I'm going to see y in a moment. Well, you can probably see y already. The y-intercept is negative 11, so we need to go down further. So negative 3, negative 2 is our vertex. Well, there's our vertex right there. Alright. Now, again, this is our y-axis, and this is our x-axis. We're going to take a look and say, let's make a table of values to help us. Well, we'll pick points around the vertex. And let's extend this x-axis a little bit here. So we're going to pick 2 points to the right, which are negative 2 and negative 1 for x. It's here and here. We'll pick 2 points to the left, negative 4 and negative 5. So again, we're picking 4 points, 2 on the right, 2 on the left. That's all we're going to do the same way every time. This becomes negative 3, negative 6, negative 3, negative 6. And finally, we plot these along with the y-intercept at negative 11. And we could plot the reflected point all the way over here. And we have our graph. And the last example in this video, find an equation y minus k equals a times the quantity x minus h squared of the parabola having a vertex of 2, negative 4 and containing the point 5, 14. So we know that that point satisfies the equation. It's on a parabola, so this is a point on the parabola itself. And here's our vertex. So right away, h is 2 and k is negative 4. And we know that from our vertex, h comma k. So we can plug those values into the equation. So we have y minus negative 4 equals a times x minus 2 squared. Well, this is y plus 4 equals a times quantity x minus 2 squared. Now we need to figure out what a is. Well, we've got this other point here. And since it's a point on the graph, it must satisfy the equation. So what we can do is we can plug it in here for x comma y and then solve for a. So let's go ahead and do that. 5, 14. So 5 goes here and 14 goes here. And then we finish off the problem, just solving for a. This is really 3. 3 squared is 9. 14 plus 4 is 18. A is just 2. So the final answer for this problem, the equation we're looking for, is y plus 4, again coming from this line right here. But then we plug the a value in, right? 2x minus 2 squared.